All right, so here we are solving a problem about a population that is at Hardy-Weinberg equilibrium. So to start any kind of problem like this, I've got two things that I always find pretty useful. And that is to start out by writing down our two Hardy-Weinberg equations so that they are right in front of us. And they are P plus Q equals 1. And that equation is saying that you have some amount of dominant alleles, P, you have some amount of recessive alleles, Q, and together they make up 100% of the alleles in the gene pool. Then the other equation is P squared plus 2PQ plus Q squared equals 1. And so that first equation is referring to alleles. This second equation then is referring to individuals, where this p squared term is referring to homozygous dominant individuals. This q squared term is referring to homozygous recessive individuals. And then this 2pq term is referring to heterozygous individuals. A possibly confusing part is that there's a 2 there, and what that is, it's accounting for the different ways that the alleles could come about. So a heterozygous individual mathematically could be considered a PQ individual or a QP individual. So if we are adding up all of those individuals, we end up with the term 2PQ to account for that. So then the second thing that I find useful is to make myself a little box down at the bottom where I'm going to be writing out whatever answers I find, whatever information I gain. And I'm going to break that up into two categories. I'm going to break it up into alleles, and I'm going to break it up into individuals. So all of the possible things that I could learn about a population at Hardy-Weinberg equilibrium are kind of spelled out by these two equations. So the alleles, I'm going to be able to find out what P is, so the ratio of dominant alleles. I'm going to be able to figure out what Q is, and I'm going to be able to figure out how common each of these types of individuals are. Okay, so now we can go ahead and look at what the problem is actually asking us. So we're talking about pea plants, and we have some information about the number of plants that have purple petals. So that's 273 of them have purple petals. So that means that 273 of them have either the homozygous dominant condition or they have the heterozygous condition. So that tells us that 276 total minus 273, 3 out of the total have white petals. So 3 of these individuals are going to be homozygous recessive. If we punch that into our calculator, 3 out of 276 is just about equal to 0.01. So if we want to find what Q is, we can take the square root of 0.01 and we find Oops, sorry, I squared that. Simply, we find that Q is equal to 0.1. So I can go ahead and bank that answer down here. And that tells us about 10% of the alleles in the population are the recessive alleles. We also know this Q squared term now too, and so we can bank that about 1% of the individuals are white-petaled individuals. And hopefully that makes sense. About 3 out of about 300. So there's some rounding going on. Okay. We still want to find all of these other terms from our equations. So I'm going to start with finding the alleles of the dominant allele. And you might know pretty quickly that if 10% of the alleles are the recessive allele, then it's going to be 90% of the alleles are the dominant allele. And we can look at our equation for alleles just to kind of draw that out for us. We have figured out that Q is 0.1. And so 1 minus 0.1 gives us that the frequency of the dominant allele is going to be 0.9, or about 90%. Okay. Now, something that sometimes trips people up is that, let's give us a different color now, is that 273 out of 276 individuals have the purple color, and what this is equal to is, again, it could be the p squared genotypes, or it could be the 2pq genotypes. And so because we have these two different terms in here, p and q, people can get kind of lost in the algebra of trying to determine those. I suggest instead, for this problem, we have figured out what p and q are, what they equal. So if we want to figure out what 2pq is, we don't need to do fancy algebra with this equation because we know the values of p and q. So we can just take our 2 times p, which is 0.9, times 0.1, and that will get us 0.18. So we can bank that answer. And our final term, p squared, again, we could do some fancy solving here, but it's going to be easiest just to use the p-value that we already found. So p squared is going to be equal to 0.9 squared, which is equal to 0.81. Okay, so we found all the information that the problem has asked us to find, and a final check that I think is always useful to do, just to make sure you're on the right track, that you've calculated things correctly and whatnot, is to make sure that whatever numbers you have are adding up to 100% or adding up to 1.0. And in this case, our numbers do add up to 1.0, add up to 100%. If it adds up to some other number, like say it adds up to 88%, you are missing something and you need to go back through what you've done in order to find out what it is. So again, with any problem, I highly recommend that you start with making sure you have your equations in front of you, and then writing out all the different terms and leaving yourself a place to kind of bank your answers as you figure them out.